Hi, I'm Tosh Dalday. This is SDG Labs. Delta x equals v naught t plus 1 half at squared, and that's a fact. With Nick's twin-turbo Lamborghini Gallardo Nera at Rockingham Deming Dragway, Force 2709. I guess that's the date. As it burns through a quarter mile pretty quickly. The display board shows you the time that it's finished, and the second display shows you the top speed at which it reached during the race. Assuming the car did not reach its top speed in the race, what was the car's acceleration? Alright, that was pretty straightforward. Simply do this. Here's the car. I know it looks like a block and it's a Lamborghini, we're saying, so it should probably be much nicer than that, but whatever. Alright, I know that it's a quarter mile, so then I got my delta x. I'm looking for my acceleration. And I have my time that it took. And I know my velocity initial is 0. Alright, so if my velocity initial is 0 and my acceleration, I'm looking for that, essentially I would use pretty much the same equation we have been using this whole time. Delta x is equal to v naught t plus 1 half at squared. What's nice is the velocity initial is 0, so therefore I don't need to use any kind of quadratic equation. And I can just solve for a, and so I would have, I'm going to change that delta x equal to r, the range or the distance or whatever, is equal to 1 half g, not g, a, t squared. So my acceleration is equal to 2r over t squared. Alright, another thing that you guys can do is saying, oh, okay, here's another question that I asked, is another thing that you guys can do is you can, the display board gave you two things. It gave you the time that it took, and it also gave you the final velocity. And your final velocity, if you want to figure out your A based off your final velocity, you don't need to use the time. You can just say v final squared is equal to v initial squared plus 2a r. Your v initial is 0, and so you got your v final is equal to the square root of 2ar. Now, which equation, actually, you know what? I made a mistake. We were actually solving for a, so a is equal to v final squared over 2r. Alright. These equations should, in theory, give you the same answer. You would just look at the video and figure out the time. You would look at the video and figure out the velocity final. I found that there's a discrepancy, that these numbers don't match up perfectly. They do get close. The first mistake I made was, I think that I assumed that it was 67.8 miles per hour. That was his top speed, but if you look very closely, there's a faint 1 in front of it. That means the top speed of that Lamborghini was when it was going the quarter mile was 167.8 miles per hour. That's pretty fast. So when I plugged in that, then it obviously came much closer. But they didn't match up exactly. And I guess the thing I kind of wanted you to think about is, which would you say is a more accurate depiction of the acceleration? Do you think that it's easier to measure the time that it takes for the car to get from point A to point B, or the speed that it takes, that it gets to? I can't necessarily trust the driver, because the driver's watching the road. He's not watching the speed gauge, you know, the odometer, or not the odometer, the speedometer. He's not watching how fast he's going, and it just says, "Oh, I've reached 167.8 miles per hour." So what? They have a radar gun? Yeah, I would say that timing is much more accurate. I mean, it's just starting a clock and stopping a clock, and that's it. You say, ready, set, go, stop. So, to be honest with you, either answer I would totally accept, but I feel like if I were asked this question, I would probably feel more confident about that answer. Alright, for part B, that one's a lot tougher. And it tripped me out because for part B, I actually made a mistake on the bus, and I was looking at it, just like, what is going on? That doesn't make any sense at all. And so I'll try to actually recreate the mistake I made, so that way what I can do is kind of show you my thought process of how I would go about doing these things. What you have to do for part B is you have to break this thing up into two parts. You can't use the equation, the one equation for the entire trip. What part B is asking is saying, all right, say that he goes at the same acceleration, and I tell you his top speed, which is like 238 miles per hour or something like that, and he goes for 10 miles. So in the measly quarter mile, he didn't reach his top speed. So you can use that one equation because he had the same acceleration through the whole thing. If it were a 10-mile race, so let's call this big D. If it were a 10-mile race, then you would have to break this thing up into two parts, because those equations only work under constant acceleration. But his acceleration wasn't constant this whole time. He accelerated from 0 all the way up until he reached his top speed, and then he stopped accelerating because he just kept going at his top speed. So technically, he didn't have a constant acceleration through the whole problem. He had constant acceleration from here to maybe here, and he had constant acceleration from here to here, but not from here all the way to here. So my question is, how long does that take him to finish? This one takes a little bit more thinking. All right, I guess the question is, how far did he go to get to his top speed? So I'm going to call a few, I'm going to label this thing a little bit better. Let's call this D1, we'll call this D2. We'll call the whole distance big D, and this will be T1, this will be T2. This is the time to get from here to here, and then this will be the time it takes to get from here to here. All right, so the question is, what is D1? How far did he go at that acceleration? That acceleration being V final squared over 2, no, let's use this one instead. 2x over t squared. Now I'm going to put a little subscript 1 on these because this tells me this is the x from the first part of the problem. This tells me the time from the first part of the problem. Oops. Those times aren't the same. So I'm going to call this T naught. That's right. All right. So I'm just taking my acceleration from the first problem and plugging it into there, because I'm assuming that the Lamborghini accelerates at the same acceleration, whether it's going 10 mile race or a quarter mile race. For that first leg of its acceleration, it's going to be the same. So in order to figure out how far he went, let's go with delta x equals v naught t plus 1/2 at squared. I don't know if I want to use that equation now that I'm thinking about it, because I don't know the time or the distance that he's moving at. I know the velocity final. He's reached velocity top speed, so I'm going to call it v with a little t down there. So let's use this equation instead. I think I use v final squared equals v initial squared plus 2a d1. That's my delta x. This is 0. Started at 0. The v final is actually vt. So vt squared equals 2a d1. So vt squared over 2a is equal to d1. All right, that's what d1 is. That's the distance he traveled. How long did that take? All right, well, in this case, that's when I used this equation. V final is equal to V initial plus A times time. This is 0, I know that, so I have V final is equal to, V final over A is equal to time. So that's how long it took for him to get there. Now this A, I would replace it with that one, and I'll do that later. All right, how much further does he have to go? How much further. Well, he has to go D1 or D2. He went D1. He has to go D2. I'm not given D2, but I know if I know D1, then I can just say, well, D2 is the total distance minus D1. Yeah, that distance is equal to this whole distance minus that segment over there. And so I have D2 is, well, that's it. How much further? Is that much further? And how long does that take? Well, he's moving at a constant velocity over here. That constant velocity happens to be 0. So really, he's moving at a constant velocity vt, or no, his constant acceleration happens to be 0. His constant velocity is 230 whatever miles per hour. So it's equal to vt equals d minus d1 over time. So if I want to solve for t, I got t is equal to d over velocity times, or vt minus d1 over vt. And let me see if I can repeat my mistake that I made, because I thought it was interesting. Let's see. I used, okay. So I said my time is actually, my total time is actually I'm not going to repeat my mistake. Why repeat it if I figure out how to do it? Is actually T1 plus T2. So T1 is V final over A plus, this is my total time, it's V final over A, or not V final, but VT over A, plus T2, which is D over VT over VT, minus D1, which is this, so it's VT squared over 2A divided by VT. So that's the D1 divided by VT. This cancels out with that, and you end up getting this. Your time is equal to VT over A plus D over VT. Let me write that here. Time is equal to VT over A plus D over VT. All right. So I started looking at this equation. I started kind of thinking about it. If he moved at a constant velocity and did the whole 10-mile race, at that constant velocity, how long would it take? Well, that one's pretty straightforward. That's like a baby physics. That's not even a baby physics problem. That's like a 4th grade math problem. But you'll have velocity moving at a constant velocity the whole distance over t. So we want to solve for t, and so you get t is equal to d over vt, which is an element of what our equation has. But he took some time to accelerate. So I think what's really interesting is if you let A be really, 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 really big, go to infinity, then what will happen is if A gets really big, then this term gets really, really small. And if A goes to infinity, then this term goes to 0. So it's saying that if you can accelerate instantaneously, immediately go to your top speed, the time that it would take would be the distance divided by the velocity that you would be moving at. See, it actually has parts of the other answers in it. What I also thought was interesting, and this kind of perplexed me, but if you let Vt be big, I'm not going to let it go to infinity, I'm just going to say let it be big, then how long does it take? Well, I guess the question is, does your time that it takes get bigger or smaller? I think the interesting thing to me about this is, usually you'll only have a variable in the denominator, and so you can say, oh, obviously it gets smaller. But in this case, you have a Vt over here in the numerator and a Vt over here in the denominator. So when Vt gets really big, this number gets really big, but this number gets really small. So does the overall number get bigger or smaller? It kind of depends, really. I thought that was really interesting. It's very rare that I see a problem like that. But anyway, here's the amount of time that it would take for you to get from one point to another. Shoots, brah! Up out!